Hi everyone. In this video we're going to talk about section 3.4, which is about the binomial probability distribution. Now this is the first sort of moment in which we're going to consider probability distributions, in this case discrete probability distributions, that aren't in a table form. So I showed you a little bit, like a tiny bit, a formula of the Bernoulli distribution in one of the previous sections and talked about how to find the mean of that. So that was in section 3.3. But pretty much everything that we've worked with so far was a table that we made and sort of were able to think through ourselves and write down the probabilities. But of course, that's tedious, and I've been hinting at this for a while, that we're not always going to use a table, because if you have, say, 500 different outcomes that are possible, you aren't going to want to use a table and write out 500 different outcomes and 500 probabilities and 500 things for the CDF as well, so on and so forth. It's just going to take too long, and it's like not possible. And so this is the point in which we're going to move from tables to functions. Okay, functions that you're used to seeing, that you like plug X in and then something happens. Okay, so they're going to look different from the functions that you're used to, but they're going to be functions nonetheless. Okay, and also we get to this point now that before we just made a table, fine. Now we're getting to what I call named probability distributions. And so this probability distribution, or rather, should I say, a family of them, has a name associated with it. So this is the binomial probability distribution. And there are a number of situations or experiments that match the binomial distribution. And so we're going to see that here. So before we talk about the actual distribution, we need to talk about the experiment that happens and what a binomial experiment looks like. It's going to be very similar to the one that we talked about before in, I believe, chapter 2 or early chapter 3, called a Bernoulli experiment or Bernoulli distribution. The only difference here is that there's more than one trial. So if you remember all the way back, I guess not that far ago, but probably you've forgotten it because it's easy to forget. A Bernoulli experiment or a Bernoulli trial is when you have only two possible outcomes, which we generally call success and failure. Okay? And then there's a certain probability of success or a certain probability of failure. A Bernoulli trial is something that happens once. A binomial experiment is a Bernoulli trial that happens a number of times. So specifically, a binomial experiment follows the following four properties or assumptions, if you want to call them that. So the experiment needs to consist of a sequence of n smaller experiments called trials. So I'm going to, I sort of pushed that even before we saw this point. It's a sequence of actually Bernoulli trials. Okay, so but there are as n of them. So there are n trials. Each trial has only two possible outcomes, which we state as success and failure until we get to the actual sort of problem. Then we can find out what they mean by success and failure. Number 3 is that there's a constant probability of success between trials. So consider the most common one for Bernoulli trials is a coin flip. Okay? And what this is saying is that each time you flip the coin, the probability that it lands heads is the same from trial to trial. And the fourth assumption or property is that the trials are independent of each other, meaning that the result of one trial does not affect the result of the next one. So we have an idea of independence. We've talked about that before, but it sort of has to be adapted to this situation here. Okay, but that means that I flip a coin and it lands heads. Great. That has no influence on whether the next coin flip is also going to land heads or tails. If these four things are met, sequence of n trials, each trial has two outcomes, constant probability and the trials are independent of each other, then it's a binomial experiment. And that means, or that indicates, that I can use a binomial probability distribution to describe the situation. Okay, and meaning describe the situation, it like matches the behavior that you're going to see, which is important because we're often going to be interested in probabilities about these types of things. And without a distribution, I can't really tell you the probabilities. So here's an example of a binomial experiment, and I'm going to go through and talk about each of those points, each of those 4 points, and make sure that this experiment meets that binomial criterion. So consider each of the next n vehicles undergoing an emissions test to either fail or pass. Okay, pass is going to denote, we're going to let S denote pass, F denote fail. Okay, great. The question is this a binomial experiment? And so the things that you need to ask, okay, and actually this is an actual problem that I could ask you, and I say, is this a binomial experiment? And the answer, like yes, is not good enough. Okay, if I ask you, is this a binomial experiment, what I'm really asking you to do is check all of those 4 conditions or assumptions. Now, it may seem obvious that those are checked, and I understand that. I just want you to write it out to make sure that I understand, that you understand. So, even if that means just saying, are there n trials? Question mark. Yes. Okay, next, n vehicles are going to undergo emissions test. Great. Two possible outcomes. Yes, there are only 2 possible outcomes. Pass or don't pass. You can either pass the emissions test or you can fail it. So pass or don't pass, and we denote those S or F. Okay, great. Constant probability of success. It doesn't necessarily say anything about the probability that a car is going to pass a emissions test here, and so we've got to we're going to assume that it's the same for each one. So there's probably an overall average of cars if we look at records for each state or each country, so on and so forth. If they do emissions testing, we probably state by state because each state is different. Okay? But there's probably some probability that's known that I can look at all the emissions tests and see how many pass, and then I have that number. That's going to stay the same, as I keep on going throughout my sample, okay, because it's known in the population. So we're going to assume true here because it's reasonable in sort of the real world, even though it doesn't say anything in my problem here. And then the 4th one are that trials are independent. Okay, and excuse my terrible handwriting. Are they? We're going to also assume that's true here because every person that comes in is probably not going to affect whether it passes or not. The last one is not going to affect the next one. You could overthink this and say, well, if the same family brings in their car, multiple cars, right, and that family does not treat their cars well, or maybe they get into a lot of accidents or so on and so forth, then it is possible that the previous one is going to affect the next one. But that's thinking too far into it. Generally, if we assume 1 car per person and we go through, one is not going to affect the other. And so, based on this, we're going to say yes. This is a binomial experiment. Okay, so that's binomial experiment. So your turn is going to be to find an experiment or come up with an experiment that meets those 4 criteria. It can be as simple or as complex as you want it. You can look one up online, whatever you want, okay? But when we come to this in class, have one so that when I ask, you have an answer, okay?